So in this video, what I'm going to cover is how to work a single sample t-test using the 6-step procedure from the Nolan and Heinzen book for my statistics course, and we're going to use R to calculate all of our statistics. So in a single sample t-test, remember that you only have one sample of data, and you're always comparing that to some population. So it's kind of easy data to work with because we really only have one kind of column of data. Now we did this demonstration in class, but I thought I would re-record it sort of all together and show you the worked answers. And then there's actually a second example on here that I don't think we did in class. So let's talk about this candidate running for sheriff. So she's claiming she's going to reduce the speed of emergency response times to less than 30 minutes, which is what we think the average is for the old sheriff. So there's your population mean. But we don't really have any old records, so we're going to have to just kind of say that there's no standard deviation, which is why this is a single T. So thanks to this campaign, she's elected sheriff. And then we have a bunch of response times, and we want to use P less than 0.05. So turn off my water fountain here, because I know people can hear it in the background. But fair warning, I am at home, so dog noises probably going to happen. Let's start with those assumptions. Now, the assumptions is the same as step 1. I used to have them in using an old book where assumptions were not part of the steps, but this is my fault for not updating this. So really, assumptions we should just write up here as step 1, and then just kind of delete this row. So what are our assumptions for a single sample T? First is the DV scale. And in theory, time is a ratio scale, right? I don't think anybody can say that it would take me 0 minutes to for the emergency response to get there, but I guess in theory it could happen. We want to randomly select, and in this case, yes, we actually could, because we have all of the records of the emergency response times, and we would be able to randomly pick some of the times. And is it normal? Well, it might be, but N is less than 30 in this case, so we don't know. So we're just going to kind of say, well, we don't know, so we're not going to assume that it's normal. In step 2 here, we're going to list our research and our null. And the research is who's the sample group. So this is the new sheriff. And we're going to compare them to the old sheriff. Simple enough. And what we're saying is that she's going to reduce the average response time. So this is going to be less than. This is going to be greater than or equal to. Now remember this combination here. So don't do less than and just equal to, because then you don't know what happens when you have greater than. So the rules are less than and then greater than or equal to. This is where we have to pull out R. So we need the mean, the standard deviation, which we're going to use as S, or little lowercase s, because that's what the book uses. The standard error, which is SM, which is capitalized just for fun, because we don't have sigma, so we can't calculate sigma M. And then we'll also need to list the population mean. We've already said that we think that that's 30 minutes. And let's figure out what some of the rest of these numbers are. I'm going to take all of this here, copy it, come over here to R, make this a little bigger, hopefully you'll be able to see it, and create a vector of data that has all of those numbers. So let's say my data equals combine. I'm just going to paste all those numbers in there. So when I run that, now RStudio, the console is not automatically up here on the right. You can change it by clicking here, or in Windows, it's like preferences or something. But I have my column of data down here. So I have 10 scores. And so I know that N is 10. Now my mean is the first thing I want to get. So I'm just going to type mean my data. That's going to tell me the answer is 28. I don't have any NA values, so I don't really need NA.rm. But remember, if it gives you NA over here, that means that something imported with an NA, and you should include this code to make sure those get excluded. So we've got 28 minutes here. Now, is that shorter than 30 minutes? Literally, yes, but is it statistically different? Let's get our standard deviation, my data. So the standard deviation is 3.71 minutes. And now our standard error. Remember, the formula for standard error is the standard deviation divided by the square root of n. But we can do the square root of the length of my data. Now, what does the length of my data do? When I run just that, it tells me that there's 10 people. Well, this gives me the square root of 10, which is around 3. And now I take my standard deviation divided by the square root of 10, which is 1.17. So that's my standard error. That's all I need for this step, because step 3 really helps you calculate step 4, step 5, and then effect size and confidence intervals. Now, step 4, what we're going to do is use p less than 0.05, because that's what the problem suggests using. Oops. So p less than 0.05, I'm doing a one-tailed, whoa, caps lock, how you doing? One-tailed test. And so I'm going to do QT 0.05. I'm not going to divide by anything because it's a one-tailed test. You could think about it as dividing by 1 because we only need that one tail. Here's where I need the degrees of freedom. So our degrees of freedom is n minus 1, which in this case is 10 minus 1, which is 9. So I got 9 degrees of freedom here. And I'm going to do lower tail equals false because I want, oh no, I want true, sorry. True. Because I do want the lower number because it's a less than test. So one-tailed less than test. Let's copy that. Now remember, cutting and pasting from words sometimes acts weird, but this hopefully won't. Yeah, so I got negative 1.83. Step 5 is to actually calculate t. There's 2 good ways to do this. You can use t.test function. And for a single sample t, what you put in is your data set. So my data. Mu. So mu in this case is 30. And then we talked in class about alternative equals, in this case, it's a less than test. And definitely conf.level, so you can get your confidence interval. And it's 0.95. Remember, a 95% confidence interval is a 5% p less than test. Let's run all that. Now it tells me what t is. I can check my degrees of freedom, and they're 9. Now that only gave me a one-sided confidence interval, which we're going to use two-sided confidence intervals because those are more common. So I could calculate t here as this 1.7 number. We'll talk about the other way to do this in just a second. But if the cutoff score is 1.83 and I only got to 1.7, my car ran out of gas before I crossed the finish line. So in step 6 here, I would fail to reject. So it's not significant or not significantly different. So 28 is literally shorter than 30 minutes, but it's not significantly different. But maybe instead of selling you on p-values, which we've kind of talked about off and on all year being a little useless, let's talk about maybe like the confidence interval of the range of possible scores and the effect size. So how practically big is the difference between these groups? Now I can get a two-tailed confidence interval by changing this to 2-sided to get two-tailed confidence interval. Hey, be quiet. Or you can use that effect size coding that I provided in class. So remember, every time you open R, if there's nothing down here in the environment window, I need to rerun all of this. So I'm going to hit Command A because I'm on a Mac, but Control A if you're on Windows, and run all of that. They give me a whole bunch of functions. But remember, this calculate window tells you all of the rules that you have to use here. We're doing single t, so I'm going to copy it over. My mean in this case was 28. My mu, or sample mean, is 30. My standard deviation is this big number. Just copy and paste it. N is 10. Alphas are p less than numbers, so 0.05, and just give me 2 decimals. Now this gives me a whole bunch more information. So I'm going to come over here and paste this. So it tells me my confidence interval of the mean, which is this set of numbers here, if it were two-sided. So that would range from about 25 minutes to about 31 minutes. It allows me to check my standard error I got a minute ago. So 1.17. It gives me my t-value and my degrees of freedom in APA style here. So that t-value I did correctly and my degrees of freedom were 9, so I'm doing pretty good. And then here's my effect size. And so my effect size here is about a medium effect. Now, what does that mean practically? Well, it's not statistically different, but it's a medium effect size. And I think when people are talking about emergency response times, any kind of effect is usually pretty important. So a medium effect size might be good enough to get that sheriff reelected. Although, I don't know if people would go for that, but you could say I did decrease times, better than nothing, right? So that would be how it would work, example 1. Now let's try example 2 down here. Maybe. There we go. And this stuff is just totally ridiculous. It's from the book. I'm going to save this and upload it on Blackboard. There we go. So example number 2 here. College seniors are falling in love left and right, right? Somehow we magically know that they fall in love 2.2 times during your college years. And we took 5 seniors, originally from this other country, but then dumped them in the US, so international students. And we asked them how many times they've fallen in love to see if students who go to college in the US are different somehow from students who go to college in their own home country. And specifically, we're trying to go with more often. So this is a one-tailed greater than test. So for our assumptions here, let's get rid of this thing, because this is step 1. Okay. Is the DV scale? Yeah, I mean, you could fall in love no times. Can we randomly select? Probably not. Because it's not really cool for schools to give up the names of their students. That's kind of against the law. So we probably don't know all of our international students. Can I randomly assign? No, because they are what they are. They're international students. And is this data normal? Don't know, and n is less than 30, so not really. I can't assume normality. It might be, but since I only have 5 people, I just don't know. So our sample here for our research and null hypothesis is this group of students, so international students in the US, sort of versus international to us anyway, right? In their home country. So it's really about the US versus their home country. And we think that they fall in love more often in the US. So this means it's less than or equal to here. So you see how the equal to is always on the null, but the research and the null have to be opposites. So I've got the greater than and then less than here. I want the same numbers. So I want the sample mean, falling in love. We know the population mean is 2.2. Need the standard deviation, standard error, and then I'll list in because I need it for step 4. So I'm going to take these 5 numbers. I can just call it my data again because I'm not using the original numbers. So I'm going to get the mean of my data. And it's 3.4, so they're falling in love 3.4 times. Right, let's get that standard deviation. So standard deviation of my data, it's 1.52. The standard error is that standard deviation of my data divided by the square root, SQRT, open parentheses, of the length, which you have to spell correctly, of my data. It's 0.068. Because that's 1.52 divided by the square root of 5, and we have 5 people here. So that makes our degrees of freedom 5 minus 1, which is 4. We're using a p less than 0.01 test from the problem here. And we have a one-tailed greater than test. And so what I'm going to do is use QT, and it's basically 0.01 divided by 1, because we only have one tail. 4 for our degrees of freedom. Lower tail equals false in this case because we want the top number. Paste that in R's, make sure it works correctly. So I got 3.75. That is a really far finish line if I round up. So that's kind of a big number I got to get to because I only have 5 people. Now we can calculate t by doing t.test of my data. Mu is 2.2. Our alternative here is greater. And conf level is 0.99 in this case. So this is one option. I think the other option's a little easier, but whatever floats your boat. So t in this case is only 1.77. But my degrees of freedom are 4. I've gotten that correct. And so I'm not close at all. Right? So I would fail to reject in this step. To get my confidence interval, I think this little code is just a touch easier. So my single sample t, the mean here is 3.4 from our problem. Mu is 2.2. Standard deviation is this big long number. N here is 5. Alpha in this case is 0.01 because our p less than 0.01 here. And k is 2. I'm going to ignore this warning message because that's based on confidence intervals for the effect size, which we're not too worried about. I'm going to check my standard error is 0.68, so I got the same number I got up here. Good. Here's the confidence interval for that mean. So it ranges from almost no times falling in love to almost 7 times of falling in love. Here's our effect size, and so it's a large effect. So while we don't have statistical significance, we do have a large effect size, which implies there might be something there. Maybe they're falling in love more here in the US, but we just don't have a sample size to really know for sure. So I am confident that we need to really sample more people because this confidence interval here is pretty wide. Right? Now my effect size is large, but I only have 5 people. So that's one of the interplays of power, remember, is that sample size is the thing that you have the most control over, and we really need a decent sample for assumptions and to be able to tell if it is statistically significant, which just gives us more confidence in our answer when we have more samples. So altogether, those two are, and this code here will be on Blackboard so that you can practice, but that's Chapter 9, which is single sample t-tests using the Nolan and Heinzen steps.